Hello, superstars. This is Mrs. Logan. I hope you all had a good time spreading kindness last week. Let's get started on today's lab. Here are some clues as to what we'll be doing today. Back out in the water. I'm coming to you from out in La Jolla Cove, and we are taking a little kayak ride. Show you. And here, there's the cliffs over there, the Scripps Pier, the shores, and back there we've got the cove. And today we are going to be doing a STEM lab on water and how scientists and researchers study that water to predict different occurrences around the world. All right, we're going to go and meet a friend of mine named Andy, who started a company that creates and manufactures water drifters that they put in water to record temperature and ocean currents, and actually they now are putting these drifters on ice floats to test how ice is melting and tracking water all over the world. All right, let's get started. My friend Andy started this company about 30 years ago. It's called Pacific Gyre. A gyre is a large system of rotating ocean currents. And Andy makes buoys or drifters to put in those currents and record data all over the world. Andy is an electrical engineer who graduated from UCSD. As a student, Andy worked under a professor studying ocean science, and together they engineered buoys and collected data such as sea surface temperatures, air pressure, wind velocity, water temperature, and sea surface salinity, which is how much salt is in the water. Andy creates a variety of different drifters that he sells to scientists, researchers, and companies around the world to study how ocean currents are moving and its impact on our Earth. Let's get a better understanding of why these ocean currents and gyres are so important.
In 1992, a cargo ship carrying bath toys got caught in a storm. Shipping containers washed overboard, and the waves swept 28,000 rubber ducks and other toys into the North Pacific. But they didn't stick together. Quite the opposite. The ducks have since washed up all over the world, and researchers have used their paths to chart a better understanding of ocean currents. Ocean currents are driven by a range of sources: the wind, tides, changes in water density, and the rotation of the Earth. The topography of the ocean floor and the shoreline modifies those motions, causing currents to speed up, slow down, or change direction. Ocean currents fall into two main categories: surface currents and deep ocean currents. Surface currents control the motion of the top 10% of the ocean's water, while deep ocean currents mobilize the other 90%. Though they have different causes, surface and deep ocean currents influence each other in an intricate dance that keeps the entire ocean moving. Near the shore, surface currents are driven by both the wind and tides, which draw water back and forth as the water level falls and rises. Meanwhile, in the open ocean, wind is the major force behind surface currents. As wind blows over the ocean, it drags the top layers of water along with it. That moving water pulls on the layers underneath, and those pull on the ones beneath them. In fact, water as deep as 400 meters is still affected by the wind at the ocean's surface. If you zoom out to look at the patterns of surface currents all over the Earth, you'll see that they form big loops called gyres, which travel clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. That's because of the way the Earth's rotation affects the wind patterns that give rise to these currents. If the Earth didn't rotate, air and water would simply move back and forth between low pressure at the equator and high pressure at the poles. But as the Earth spins, air moving from the equator to the North Pole is deflected eastward, and air moving back down is deflected westward. The mirror image happens in the southern hemisphere, so that the major streams of wind form loop-like patterns around the ocean basins. This is called the Coriolis effect. The winds push the ocean beneath them into the same rotating gyres, and because water holds onto heat more effectively than air, these currents help redistribute warmth around the globe. Unlike surface currents, deep ocean currents are driven primarily by changes in the density of seawater. As water moves towards the North Pole, it gets colder. It also has a higher concentration of salt, because the ice crystals that form trap water while leaving salt behind. This cold, salty water is more dense, so it sinks, and warmer surface water takes its place, setting up a vertical current called thermohaline circulation. Thermohaline circulation of deep water and wind-driven surface currents combine to form a winding loop called the global conveyor belt. As water moves from the depths of the ocean to the surface, it carries nutrients that nourish the microorganisms which form the base of many ocean food chains. The global conveyor belt is the longest current in the world, snaking all around the globe, but it only moves a few centimeters per second. It could take a drop of water 1,000 years to make the full trip. However, rising sea temperatures are causing the conveyor belt to seemingly slow down. Models show this causing havoc with weather systems on both sides of the Atlantic, and no one knows what would happen if it continues to slow or if it stopped altogether. The only way we'll be able to forecast correctly and prepare accordingly will be to continue to study currents and the powerful forces that shape them.
So now I'm getting a much better understanding why these drifters and all the data that they're collecting are so critical. So NOAA stands for the National Oceanic and Atmospheric Administration. And I remember seeing a ship while I was out fishing a few months ago that had NOAA on the side of it. I looked up the mission of NOAA on my computer, and I was excited to see their first objective is to understand and predict changes in climate, weather, oceans, and coasts. They also like to share that knowledge and information with others. Lastly, they want to conserve and manage coastal and marine ecosystems and resources. Can you start to see why collecting all the data from these drifters is so important? Check out this cool program run by NOAA.
Covering 70% of the Earth's surface, the ocean plays a major role in our climate, weather, and living conditions for plants and animals. Through the NOAA Adopt a Drifter program, kids are learning about ocean currents in real time as scientists collect and analyze ocean data. First, drifting buoys are deployed from ships at sea. As they're carried along ocean currents, drifters measure and transmit sea surface temperature data and positioning coordinates via satellite for about 400 days. Surface ocean currents are a continuous, directed movement of ocean water, generated by forces such as the wind and steered by the Earth's rotation. Surface currents carry heat from place to place, which affects our planet's climates. Students follow their adopted drifter and analyze the sea surface temperature data in their classrooms as it's posted online. The data are then used by both ocean scientists and students to track warm and cold currents. Understanding where and how fast the warm and cold currents are flowing is useful in several ways. It helps provide more accurate weather forecasts, track oil spills, and learn where drifting plants, animals, and migrating species travel. Adopt a Drifter is science in action, giving kids an inside view of how the ocean connects us all.
Let's take a closer look at one of the drifters Andy makes. So if I were to order a MicroStar drifter, it would come
and
packaged
you ordered
just
it
like
in a
this.
bag like this.
Uh-huh.
The surface load is a little protective neoprene bag. And then you get your drifter like this. To deploy the drifter, you would pull the magnet off.
Mm-hmm.
That turns it on. It's in the low power mode that turns into deployment mode. And you open up the drug, pull it out, so it snaps, and then you carefully place it in the water.
All right, and this orange, this circular part, this will stay
This will
above.
float it about the equator. And this has a GPS receiver, a satellite transmitter, and in this case, it has a temperature sensor. About 10 years ago, we started doing a lot more work in the Arctic, and so a lot of our instruments end up in the Arctic these days because it's a kind of a hotbed of activity, scientific, because of climate change, everything seems to happen in the Arctic first.
Mm-hmm. So one of the fun things about being an engineer is you have to figure out how things will react. So these drifters in the Arctic can be dropped from hundreds of feet from an airplane or a helicopter. So Andy would go up on the roof and throw them off to see if the buoys could withstand the impact and still function properly. Check out this incredible experiment being done in the Arctic right now.
Mosaic will be the biggest and most complex experiment in the Central Arctic ever. We'll be making observations that cut across the full Arctic system, sampling the atmosphere, sampling the ice, sampling the ocean, and how they interact. We'll be on a German icebreaker frozen in the Arctic sea ice, and we'll have scientists from 17 nations engaged in a variety of scientific activities. In September, we'll arrive in the sea ice. We'll be setting up and we'll be racing the sun. As the sun is setting for the season, we'll be trying to install our equipment on the sea ice. As the wintertime evolves, it'll be very dark. There'll be a challenge to make our measurements, but it's really important then because we had very few observations in the cold, dark winter season. As we transition towards spring, the sun will come out and the whole system will change in response to that, with the sun changing the energy balance at the surface, changing the sea ice, changing the biological activity that's responding to the sunlight. As we transition towards summer, this is the peak of the melt season, we have a lot of change then. We have 24 hours of sunlight that's putting a lot of heat and energy towards the surface. It's melting the sea ice, it's melting the snow, it's forming melt ponds. And then we transition at the end of summer back into fall where we started to bring back for the full annual cycle and understand how the processes come full year round.
The Bering and the Chukchi Sea in the past 2 or 3 years has been ice-free until the middle of December, which has not been observed in the climate record. The Arctic climate is warming much faster than the rest of the globe. And the Arctic amplification can happen for many different reasons, because the ocean's warming up, because the sea ice is getting thinner, because the atmospheric structure is changing, because the cloud cover is changing, and every climate model does it differently. And the data is very limited, even in the Chukchi and Bering Seas, where we do have a lot of shipping and transportation and fishing. We need to have detailed measurements of the fully coupled system. There was a similar campaign that happened about 20 years ago called Sheba, and we learned things during Sheba we had absolutely no anticipation of knowing, such as the fact that there was liquid in clouds at temperatures down to minus 40 degrees Celsius. So what I am mostly excited about is that we're going to learn things that we cannot anticipate at this time.
So when Andy and his team of engineers are preparing one of their drifters to go to the Arctic, they need to take some very special precautions. It gets really cold there. Look at how they devised a way to put their drifters in a 40-degree below zero chamber.
100 pounds of dry ice in there, and then he's got fans inside that circulate the air, and then we have a temperature sensor on the side here. We can see how just an old analog temperature sensor, and we can get that down consistently to like minus 40 degrees. It's a low-tech solution for a low-tech problem.
Oh yeah. It's like a big refrigerator, freezer.
Right. Yeah.
And then you got the fans that circulate.
We'll put a shelf, we'll put the drifters on a shelf, and we'll circulate the air with the fans.
How do these drifters get funded?
So most of them are purchased by institutions around the world, that research institutions, for instance, the Scripps Institution of Oceanography, and those scientists apply for funding from the government typically. So that would be the funding for most of the drifters here comes from NOAA and the National Science Foundation, the Office of Naval Research, so that the U.S. by far funds more science in the oceans, in this world, probably this world of ocean physics, than any other country. I mean, 100 times more. And most of that is through organizations like NOAA, like I mentioned.
These drifters have been so helpful with giving scientists vital data to help plan for the future. But Andy also shared with me one other way that they're helpful in the wake of a disaster. Let's say an oil spill occurs in the water. Oil spills have disastrous impacts on the coastal ecosystems, human health, and even the economy. So drifters, if placed near the epicenter of an oil spill, can help cleanup efforts by tracking where the oil goes as it moves quickly into open water and into the global ocean conveyor belt. So for experiment number 1, you're going to be making an ocean in a jar. Supplies you'll need for this beach activity are some shells, sand, water, and any other beach treasure you may find. Maybe you have some seagrass or some little ocean animals. If you'd like to add a little glitter or a couple drops of blue food coloring to your jar, go right ahead. All right, our second experiment has to do with looking at how cold and warm water react when they come in contact with each other. So I put cold water into a pan, and I'm going to stick some blue food coloring in it. So I also put in a little turtle and a shark, so it looks kind of like the ocean. Although my turtle is larger than my shark, but oh well. Then you're gonna have to boil some water. So I'm boiling my water, and I'm gonna put it in a little coffee cup with some red food coloring. All right, you might want a grown-up to help you with this part. Make sure you pour it into a coffee mug. Turn off the stove and put in some red food coloring. Now, very slowly pour your hot water into the cold water and see how they react. For our third experiment, we're going to simulate an oil spill. So I have a pan full of ocean water, and I'm going to pour some oil, which is going to be our oil spill, and some blue food coloring into this container. Now, you'll see, if you look in here, The oil and the food coloring, I'm gonna add a few drops more. They don't mix entirely, but it's gonna show us exactly how it spreads once we pour it into our ocean. Okay, now just like in real life, oil does not just stay on the top of the water. Look at how some of it is going down below in a mixed layer. So your job now is to try to get the oil out of the ocean. You can use multiple ways. You can take a spoon and try to carefully skim off some of the oil. That's what they do in real life. They take skimmers and they try to get off some of those chunks of oil on the top. Look at how though sometimes it actually breaks apart and goes down into that mixed layer. You may also try to take some cotton balls to absorb it. See if you can absorb some of that oil and the food coloring. Squeeze it into here. And then also you can look up how scientists and cleanup crews use dispersing as a means to clean up oil spills. All right, scientists, have a great week, and I'll see you later. I hope you enjoyed learning how these drifters are collecting vital data to help us understand our oceans and their effect on our world.